I'd like to talk to you about a second vector form of Green's theorem. So let's take a look at or consider the following fact. So let's take a look at this. Here's your xy plane. Let's pretend we have a region D here enclosed by a curve C. So we're moving around a positively oriented way. And what we can do is we can focus in on any point along this curve. And at this point here, there certainly is a tangent vector. Okay, and we've already discussed what this line integral of f dot dr really is, right? So what we're going to say instead is, we're going to become interested in today is, what can we say about this normal vector here and its relationship to maybe some double integral over the region D. That's sort of what we're interested in. All right, so let's start to write some expressions down and so forth and see what we're doing here. Okay, so if we just remember during all this that r of t is x of t I plus y of t j, and that's the function that describes the motion around curve C. This is sort of the equation of curve C. Okay, so the unit tangent vector then is the derivative in the x direction there over the norm of the whole vector here plus the derivative in the y direction, again, over the norm of the whole f. So that's your unit tangent vector function. This gives us unit tangent vectors at any point along the way. All right, so what's the normal vector look like? We need a vector that's perpendicular to that. So here's an example of one that does it. Okay. So here you are, I minus x prime of t over the norm of r prime of t, j. Now, if you're wondering, how do I know that's perpendicular, just take the dot product, and you'll see. Take a look, think about multiplying these things together. If you multiply these two components together, and then multiply these two components together and add them, they'd be the same thing, but opposite of each other, and you get the scalar quantity 0. Okay, so what we're going to do now is we're going to concern ourselves with, instead of f dot dr, which is sort of the work in the direction of the tangent vector, we're going to concern ourselves with this line integral. We're going to say, what does this thing equal? F dot n ds. Okay, well, we can say, we're going to parameterize this, it's from a to b of f dot the normal vector, which now f could be written as a function of t, and so could n, we know, as a function of t. So we'll say that. This means as a function of t. And then ds is just the norm of r prime of t dt. Okay, so let's be a little bit more specific about what this part of the expression looks like. Just this part by itself. So a little bit of algebra here for a while. It's a little bit of a ride, and then you'll see something nice at the end. So we have the integral from a to b of p of x of t, comma, y of t. So I am taking p, which is the first component of f, and parameterizing it with respect to t, times y prime of t over the norm of r prime of t. Well, if you, okay, just keep in mind what this is. That's the first component of the normal vector. And it's been dotted with or multiplied by the first component of the vector field f. But just to be clear, just in case, the vector field f is equal to p of x comma y I plus q of x comma y j. So that's what that's equal to. All right, so then we're going to do the following. It'll be minus. That minus comes from the dot product of q with the second component of the normal vector. So you have this, x of t, y of t. We just parameterize q by plugging in x of t, y of t into x and y, multiplying that by x prime of t over the norm of r prime of t. Now let's just not lose track of things. Why is that true? Because that's coming from this. This is the second component of the normal vector n. Here's the first component of the normal vector n. And I did a dot product with those two things. And this expression, okay? And this fancy notation just means, hey, look, I'm not writing p of x, y. I'm writing p of x of t, y of t, because x and y are both functions of t. How do I know that? Because I know this, which tells me that x is a function of t and y is a function of t. Okay, lot of review and so forth. Now don't forget, this whole thing gets multiplied by ds, which we already said was the norm of r prime of t dt. All right, so you can kind of see if I distributed that across, these denominators would cancel out for us, and we would simply get the line integral from a to b of p of x of t comma y of t times y prime of t dt minus q of x of t comma y of t times x prime of t dt. But that we can write this way in a more compact form if we were to sort of, like I said, we're going to like unparameterize it, I guess we'll say. P dy, right, minus q dx. Why is that? Here's dy right there. There's p. This is q. That is dx. So that's what we get. But we know the following. We know by Green's theorem that this is equal to the double integral over the region enclosed by these things of partial p partial x plus partial q partial y dA. Okay, that's Green's theorem. You know, the minus turned into a plus because in the original one it's plus and it turns into a minus, and so forth. And these are sort of like in a backwards order a little bit, so just move it around, and you'll see that that's the case. But this thing here, you should look at and recognize. What is that? That is the divergence of f. So what we now have shown is that the line integral around the curve C of the vector field dotted with the normal component to the normal vector to the tangent vector is equal to the double integral over the region D of the divergence of f of x comma y dA. So there you go. There's a second vector form of Green's theorem. What does this say? Well, this version says that the line integral of the normal component of f along C is equal to the double integral of the divergence of f of the region D enclosed by C. Okay? So what is that saying? It means, I guess, sort of like this. You have a curve C defined by, this looks like it's got a kink in it. It should be a nice, smooth, differentiable curve here. Let's go the other way, actually. Let's go this way. All right? And what we've said is we've sort of, by finding the line integral, we've added up all these normal components along the way, sort of found the sum of all those things. That's what this line integral does. And what we're saying is that sum that you get is equal to the divergence associated with every point inside this region that we've been calling D all along. The sum of all those divergences added together would be the same as the sum of all these normal vectors, these outward normal vectors to the curve. So it sort of makes sense that we can get the total amount of divergence or flux through this curve two ways. That's what this is really saying. Okay, thanks for watching. Okay.